BornHack. It's Poul-Henning, who's going to do 2 talks, one about his new house and one about the ESO telescope project. Let's give a round of applause for Poul-Henning.
You should hold that until I'm done. In 2012, we did a prototype for ESO, the European Southern Observatory, for adaptive optics for large telescopes. Traditional adaptive optics have been racks full of DSPs and FPGAs and stuff like that. And then 5 years later, the company that did it doesn't exist anymore, and 10 years later, they can't get spare parts. So they wanted to try to do it on regular computers, common off-the-shelf computers. We just won a second round of this. Now we have to build the real thing. So this is a little bit of a talk about what the ESO ELT is, what adaptive optics is, and what we're doing about it. So this is actually Newton's first mirror telescope. The movie there is a professor from Nottingham University who has a series of periodic videos about the periodic system. Because the mirror is actually not glass, it's a speculum, a particular metal alloy. The interesting thing here is this telescope is 5 centimeters diameter, 2 inches. William Herschel started making bigger mirrors because bigger mirrors means you get more photons, which means you can see more things. And we've been building larger mirrors ever since. This is the state of the art at this point. This is the 8.2 meter telescope, or mirror for the VLT telescopes ESO built in Chile. They built 4 of them to try to do interferometry using the light from all 4 telescopes. You get a virtual telescope and stuff. That took 25 years to get that to work. But this is about as large a mirror as you can do in one piece. If you try to make a mirror that's larger than 8 meters in diameter, it kind of gets wonky on you. And 8 meters is, I guess this tent is probably 10 meters across. So we're talking really big slabs of glass here. So what ESO wants to do now is build the really large telescope. The original project was called OWL, the overwhelmingly large telescope. And that was supposed to be 100 meters in diameter, which is sort of like a soccer field. They did the math and found out that we have to build it from something we don't know what is, because not even carbon fiber would be able to hold a mirror like that, stable to within a couple of wavelengths as it turns to follow objects in the sky. So they downsized the project to 42 meters because this was really a telescope about finding planets, livable planets. So this is about life, the universe, and everything. So 42 meters sounded right. And the cost came out around 2 billion euros. And they were told, no way. So they cut about 1 billion euros from it, cut it in half, and they end up with a diameter of 39 meters. This will be a segmented mirror, and there's a mock-up on the grass there. It will consist of close to 1,000 mirror segments, each about 1 meter, all tracking the same direction. If you point this telescope at the sun, you get 1 megawatt of sun energy, which means that your secondary mirror is gone. So don't do that. ESO has used, as a matter of principle, about 10% of their budgets for prototyping. So there's around 100 million euros used on prototyping this thing. These are some of the prototypes. The yellow thing behind there is actually one of the segment holders that will hold probably in the end 7 segments of the main mirror in one unit like that. The one here in front is the tip tilt mirror. It can move in 2 directions to take the global corrections of the wavefront out. It's also a very high quality subwoofer as it goes to close to 1 megahertz. But you have to stand right at the right place to hear it. Otherwise, it's kind of funky. So we did this prototype in 2012, where we take 10,000 floating point numbers, multiply them by a registration matrix, which is also 10,000, then multiply it by a projection matrix, and then we get 6,300 floating point numbers out that's used to correct all these mirrors. And the footnote about this is we have to do it 500 times a second with very low jitter, 20 microseconds jitter on the packet we send out. And we did that on a cluster of Dell computers, 56 core Opteron machines. And we did it well inside specification. So it's possible to do this. So foundations are the lowest part of a building, and they're making the foundations for the telescope now on top of a mountain, which is sort of ironic, I think. But what is all this adaptive optics stuff? So photons are weird. We used to think about photons as this particle that runs in a straight line, but that's actually not what's happening. If you put up 2 microwave antennas, you need a volume of space. It's not just enough to have line of sight. A tree that does nowhere get near your line of sight can still severely impact your transmission because the actual electrons of your, or the electromagnetic field of your transmission takes up what's called the Fresnel volume. And you can calculate that. So the interesting thing about this is if we start out with a mirror of size 1, then we're doing a windowing effect on the incoming wavefront, which means we get all these artifacts. First order, second order, third order. So if we make it twice as big, the frequency increases as well of these. And that's why the larger your telescope, the sharper your images. So a larger telescope can see smaller features out in space. So if you want to see a planet next to a star, you want a really large mirror. That's the basic physics of this. If your mirror has a secondary structure sitting in here, then you get different, it's kind of hard to see it, but you get different disturbances in your wavefront. If your mirror is not round, you get spikes. If you have a segmented mirror, things get really weird. So getting as sharp as an image as possible is not as simple as one would think. But the other problem is that between the mirror and the star we're looking at is a lot of air moving around. And if your telescope is 2 inches, you're looking through a pretty homogeneous slice of air out there. But once your mirror is 39 meters in diameter, you have turbulence inside the cylinder of air you're seeing light go through. And that's basically why we see stars sparkle. We see a star flickering around, and that's the air moving the image of the star around because the air has different densities and stuff like that. So if you take a short exposure, you get this kind of speckled image. If you take a long exposure, you get this kind of woodsy things. But if things were perfect, you would get a dot. Adaptive optics is about getting that dot instead. So the thing you do is you have a wavefront coming in from the star. You have a mirror you can bend. You split some of the light out to what's called a wavefront sensor. Then you figure out how disturbed is the wavefront here. Then you bend the mirror to correct for that. And then your science instrument will get a perfect image. That's the deformable mirror for the ELT telescope prototype. So it's a very, very thin mirror with 4,000 actuators that can pull or push a few wavelengths on the glass. So the glass can be pretty much any shape you want it to be to compensate for the incoming wavefront. They installed adaptive optics on the VLT-4 telescope in Chile, the 8-meter telescope. And this is with a Neptune with and without adaptive optics. This is the kind of difference we're talking about. The ELT telescope, being 4 times larger, will basically be useless without adaptive optics. It will just be one fuzzy thing you see. So it's very important there. The interesting thing about this one is this is Neptune seen from the ground with adaptive optics, and that's seen from the Hubble telescope. We're basically compensating out the entire atmosphere disturbance. And since the mirror is larger, we get better resolution. So the Wavefront Sensor is this weird kind of thing where you have a lenslet array, simply an array of a lot of small lenses. And then when you put that slightly out of the focal plane and project it, you get an image that shows how the wavefront is disturbed for each part of the main mirror. So the red dot here says that at this place on the main mirror, the wavefront is disturbed this direction. So you get an x and a y coordinate for all these points. And then from that, you have to figure out how to bend the mirror in the other end. And that's the math we're supposed to calculate or perform. We're not coming up with all the coefficients. The last thing missing is that you need your wavefront sensor to look at a guide star. And if you can use a natural guide star, that's obviously best. But it has to be pretty close to a science field, and that's not always the case. So they've come up with shooting lasers into the sodium layer. It's not actually a layer, it's just about 10 kilometers in the upper atmosphere where there is some sodium. And if you hit that with the right wavelength, it lights back. So you can make an artificial star that way. And that's why many pictures of modern telescopes, you have these lasers shooting out of them to generate artificial stars. And sometimes they get a phone call to turn the laser off now, because there's something out there that doesn't want to look into it. And they get told, turn it off for 7.5 minutes, and they turn it off for 7.5 minutes, and nobody gets mad about anything. It's pretty strong lasers, all things considered. So the thing we're supposed to do is we're supposed to take 6 wavefront sensors, which takes 800 by 800 pixel images 500 times a second in 16-bit resolution, black and white, and do 700 gigaflops of calculations on them, and send the results out to 4 deformable mirrors, which will bend the wavefront into shape. And we're supposed to tell them what goes on inside it to the tune of 3.5 gigabit telemetry along the way. And this is basically supposed to be a Lego brick tool they can use to build the telescope and the instruments that go with it. And everything in this is a parameter, which is a neat little thing. So the limiting factor for us is the memory bandwidth. The level 3 caches are not big enough to hold these huge matrices that we're multiplying. Not quite. In a couple of years' time, we'll probably see chips with level 3 caches that can do this in cache. And then they can just buy a new Dell server and put it in and run even faster if they want. So the hardware criteria for us is the number of memory buses, which means that we're looking at the AMD EPIC chip. And that's a really interesting chip. We have a machine right now with 2 sockets, 64 cores, and 16 memory buses. Somebody released a benchmark on his blog a couple of days ago where they had an EPIC server and they tried to run it and it was like 30% faster than a comparable Intel machine. And that's basically because they have twice the number of memory buses. But this is actually a very beautiful design. AMD's Project C is 1 chip, and they have like 66 products coming out of it. And I think they added a couple this week too. So the EPIC, the Threadripper, the Ryzen, they're all the same chip, the Zeppelin chip. And they can sell chips even though most of it doesn't work actually. They have a very long list of units. At the top end, you have 4 perfect chips in a single socket. That's the EPIC 7601. It costs $4,000. You get 64 threads, 32 cores, 8 memory buses, and 2 sockets. Then you have 7 other dual socket products. And then they have the lowest dual socket where you have 4 of these chips with a lot of defect cores. So you only get 16 threads, 8 cores. That's a quarter of the number of cores. You still get 8 memory buses. And you can get it for $475. That's a very interesting machine. It has a lot of memory bandwidth. And it's very cheap. So then we get to single socket systems. So you have 4 almost perfect chips. The only thing that doesn't work is the buses to connect them together in a dual socket system. $4,000 again. It ought to be $4,100 maybe. Then there's 55 other products. And then you have the bottom line where you have a really rubbish chip, which they sell for $109. Most of that chip doesn't work, but you get, 4 cores, 4 threads, 2 memory buses. So I tried to map out, this is the Zeppelin chip. The black bits can be defect and they can still sell a product. That's really good design. It's more than 50% of the area can be defect and they still have a $100 product. So AMD is going to clean Intel's clock until they usually shoot themselves in the foot. That's how AMD does it. That's a very interesting design. But then you start reading the hardware specs really carefully, and it says this machine can only operate up to 10,000 feet. And it's like, how tall was that mountain? Oops. So have you ever heard about extreme Wikipedia editing? This is how you edit Wikipedia. So as long as they install the computers at the ground floor, we're fine. Frederick P. Brooks in the Mythical Man Month wrote that writing a program, if we set that to effort 1, you write a program to do something for yourself. 1 effort. If you want to make it a product, you have to document it and you probably have to fix some of the bugs. So that's 3 times as much work. If you want to make it a systems programming product, which is, it's a kind of old term, but what he means is a configurable program product, add another factor of 3 on top of it. And then if you want to make it international, so it can talk Japanese, another times 3. Portable, secure, user-friendly, multiply by 3 each time. So in this case, everything is a parameter. So we're coming down here to make this possible for everything to be a parameter. How many wavefront sensors? That's a parameter. How big are they? That's a parameter. How many mirrors? That's a parameter. So writing code that handles dynamic sizing, we've done that for ages. And that code is where we find most of the programming bugs and most of the security issues. Buffer overflows, just for the most trivial one of them. We have some very large parameters. The control matrix, the largest one, is 230 megabytes, and it can change once per minute. And we have to inject this 230 megabyte thing into this tightly choreographed real-time system that runs 500 or maybe 700 times a second. We have also some that changes every work cycle. That's simply a real-time disturbance that gets sent in for calibration purposes and stuff. And some of the static parameters have really heavy implications for the sequence in which we can do the operations. The order we get the pixels from the camera determines the order we can start the calculations, the sooner we can be done, and so on. And yeah, an 800 by 800 camera, that's not really anything these days, is it? Except it takes 700 frames per second, progressive readout, and has a direct digital readout. It doesn't come out with an analog signal that somebody digitizes. It comes out digital on the fly, and the noise is about 3 electrons per pixel, which means there's no noise, and has 90% quantum efficiency, which means it gets all the electrons you basically can get. One of the things I found interesting about it is that they read it out in parallel, so they have a lot of AD converters. How did they do that? And that's a really neat trick. So the signal comes from the optical part here. They have a preamplifier, then they have a comparator. This is each pixel column. So they have this ramp signal coming in, one single ramp signal that goes to all the pixel columns. And then they have a gray code that corresponds to the ramp. So whenever the ramp crosses the signal here, they latch the gray code. A gray code is like a binary code, there's only one bit that changes at a time. So you don't have any, when you change from 7F to 8.0, you would have all 8 bits changing in a byte. And getting all of those to change at the same time is very hard. In the gray code, only one bit changes at a time. So it's always stable that way. But basically that way, they can do a AD conversion on 400 pixels at a time in parallel and ship them out serial as bits at full speed. That's really brilliant thinking here. And this is this is what they dream about. The one they're talking about here is not the one they're going to use in the first generation instruments, but that will be what we see in the next generation. And that's 4 times the number of pixels we're looking at now. But basically, they built this chip, the NGS chip, which is 1/4 of it. And then the plan is to just build 4 of those and fit them together in the focal plane of the instrument. Our current evil idea is that we'll take all the static parameters into a Python program and have that program spit out C code instead of having the C code dynamically size. We can size all the arrays statically at compile time, let the compiler deal with them and optimize them. And there won't be a configuration file, there'll be a Python program, which is the configuration file. So for instance, you want to load this map from a FITS file, you load it from a FITS file. But this is a Python program, so you could also have a loop that sets up an array in some systematic way and so on. We suspect this might be a hard sell, but we plan to sell it anyway. It's not the way they used to think at ESO. We think of it as just-in-time compilation. It's not just-in-time the way we do it with Java computers and Java virtual machines and stuff like that. But at the startup time, we generate code we're going to run. And some of you will know that this idea has been exploited in Varnish. The Varnish configuration file is compiled to a C program, which is compiled to a shared library, which is loaded in and executed at machine speed. And that's where we got the idea, basically. But there's a lot of advantages for us here. We have to write a ton of test files. And normally you'd write a program to create the test file, and then you have version control on the program and on the test file and blah, blah, blah. In this case, we just have the Python program that generates the test data and version control on that, and we're done. We may even be able to do a Python version of the numerical model and use that for fuzzing tests. Send the same input to the Python code and to the real code, and see if we get the same results out at the end. Within the Python code will be using doubles, whereas the real code will only use floats. So there'll be some routing effects we'll have to look at, but we'll see if that works out. So that was the ESO ELT project. Any questions?
Thank you. When you take the light off in the ELT to assess how to deform the mirror, what fraction of the signal do you siphon off that way?
So that illustration I used here is not the way they're going to do it in this case. This is when you go to the optician to have your eyes measured, you're actually looking into one of these wavefront sensors, and that's the way they do it with a half-silvered mirror. In the ELT and generally in astronomical telescopes, what they do is you have a science field, and then you have a periphery, and you'll use the periphery for the adaptive optic sensors. So you have these sort of robot mechanisms that can, in a polar coordinate system, put the sensor where the light is, so to speak. And usually the science instruments will be designed either to only use the central part of the scope, or to accept that there will be these devices sticking into the edge. And you'll have to deal with that in the science planning. There's a very heavy-duty application running to schedule observations, because you have a lot of constraints. Some things have to be observed at a particular period of some binary star or whatever. You cannot put the telescope so that if something breaks down, the sun will come across the focus within at least 12 hours, preferably more. Lots of constraints that way, and the adaptive optics shading is one of them. That adaptive optics is possible, and that it doesn't shade the science target and stuff like that. And of course, all the astronomers thinks that their particular observation has priority 0, which is a major part of the application. There's one down there.
So the Python program generates the C program, which is the 200 something megabyte of parameters?
No, the parameters are transferred as UDP packets, but there's the static parameters which will not change while we're running. And that would, for instance, be the number of wavefront sensors and how large they are, or how many mirrors are active in this configuration and stuff like that. And that's what the Python program takes in and compiles a version, or generates parts of the C code, compiles the entire thing to give a application that's optimized for this configuration.
And how big is that C code, roughly?
I think the last prototype we did was around 100,000 lines in total, including test harnesses and stuff. And we don't expect this to be particularly much larger, because we use the Python code to take a lot of the if-diffing out of it.
And it's not so time critical because it's at startup.
That's only startup, yeah. So 10 seconds, fine.
Yeah.
I mean, starting an observation on a telescope of this class will probably take close to 10 minutes. Between getting it into position, getting it stabilized, getting it locked, getting instruments, and so on. On the VLT, I think they can rapid fire observations they can do in something like 7 minutes, excluding the slew time to move the telescope over there. But it will be more on this one, because simply moving the entire telescope, you'll have to wait for it to stop wobbling. It's a very large structure.
Yeah, so the concept of compiling just in time, I've also seen that with TCC by Fabrice Bellard.
Yeah.
Yeah, so he did a fun demo of that with the kernel.
Yeah. But it's I expect we'll have some comments on this from ESO on Wednesday, because we kind of hinted to them early that we'll come up with a proposal doing it this way, and there was some, what? Kind of reactions. So we expect that some people have gotten their knickers in a twist about it, but we think it's the right way to do it in this case, because what they want, so part of this is that they have the telescope and then they have the instruments, and the instruments will change over the lifetime of the telescope. The VLT telescope is on the 3rd generation instruments now. And part of the adaptive optics is in the instrument. So they don't want to have to start from scratch every time they plan a new instrument. They want something that can say, okay, this instrument has these parameters, here's a file, run. And we think doing the Python thing is the right way to attack that problem, to get maximum software quality out of it.
Yeah, and there is prior art, so it's not like an exotic
No,
thing,
not at
right?
all. Not at all.
So this is a very latency sensitive problem, right?
Yeah, this is basically a feedback loop.
Yeah. So how do you get data into your Dell computers fast enough?
1 10 gigabit
Ethernet
from each wavefront sensor, and it's basically chock full of packets. I think they're using something like 60-70% of the bandwidth for each wavefront sensor.
All right.
Okay. So the other half talk I brought is about the house I built. We had the luck that a plot of land across the street came up for sale from a bankrupt developer. A quite large plot of land, quite cheaply. And we bought that in 2012, and then we built a house on it. And this is probably most relevant for Danes, but the experience of building a house as a nerd. So one of the first things that's interesting is we have all these open geodata in Denmark, which you can use to find out if you actually built the house the place you thought you built it. This is the latest orthophoto images from this spring. And it's taken from a slight angle, but it looks like the house is basically where it's supposed to be, under the white line. I use these geodata images quite a lot during the planning and stuff like that. I can highly recommend to play with them. There's a lot of fun. This house is built to the Danish Building Code 2020, which means it should basically not use energy under normal circumstances. It looks like our heating bill will be around 4,500 kilowatt hours per year. And this is a plot I did where I have the outside temperature on the x-axis and the number of kilowatt hours per day we used. And we get a pretty good correlation that says we're using 1.3 kilowatt hours per day for heating for every degree we have to heat the house. That's actually pretty amazing considering that this is a house where people open the doors and take showers and stuff like that. The 20 building code in Denmark is pretty highly insulated. You end up with exterior walls that's 0.5 meter thick, which gives a lot of place in the windows for plants. But it actually works out. You basically don't use any heat in the house at the end of the day. This is an expense of around 4,000 kroner a year at the current rate of electricity for electrical heating houses. This is a ground heating system. If I look at what we use our power for, first we have put solar panels on the roof, a 3 kilowatt system, which I've been monitoring our electricity use for a lot of years, so I had a lot of data to simulate with. And I found out that the hotspot, the sweet spot would be around 2,400 kilowatt, 2.4 kilowatt solar panels. So I rounded it up a bit to have a margin for adding air condition to global heating later on. We used a little more than half of the solar energy we produced. The rest we sold back to the grid. And this is including my company that runs a bunch of computers and network and electronics constantly. For a normal household, you would probably only use about 1/4 of the solar power you generate inside the house. The rest will go into the grid. Because basically, when the sun shines in Denmark, you're at work. And when you run the dishwasher and the dryer and the washing machine and stuff like that, it's dark outside. So solar cells is a really good idea, but don't expect to use electricity yourself. And no, I couldn't get batteries to make sense. I did a lot of math on batteries. It doesn't make sense. Electricity is too cheap and the feed-in rate is too good in Denmark for that to make any sense. It will change as the price of batteries come down, but at this point, no, it doesn't make sense. So this is what we actually use the electricity for. So the ground water heating system uses the largest majority of it. And my company uses quite a lot of power also. This is the cooling unit in my company. So one of the disadvantages of having a new house that's well insulated is you cannot find a cupboard somewhere and stick a server in it. Trust me on this. It won't work. It will get very hot. A room 2 by 2 meters will take 2 watts to heat 1 degree. So if you stick a server in there with 120 degrees, it will get hot. Very hot. So I have a cooling unit in my company. Otherwise, I couldn't run anything. And that's a 16 square meter room. And it would just get too hot without a cooling unit. If we take the company out of the picture, it looks slightly different. So this is the light, general whatever we plug into the outlets in the house. This is the kitchen. This is the washing machine, the dryer, and the dishwasher machine. And the last one is the stovetop where you cook your food. So it seems like sort of a 50-50 thing there. And then I have a quiz. So we wanted to get internet. And there's about 200 meters from the public road to our house. So I called the antenna company and said, that will cost 19,000 kroner. And I called the phone company, they said it will cost 30,000 kroner. And I told them, and put up my own cabinet next to the road. And we run 10 pair of telephone cable, a half-inch coax cable, and 12 fibers down to the house. That cost me total of 9,000 kroner for all of it, including the cabinet. And then I called the phone company and said, I want an XDSL in that cabinet. And that cable is literally there. This is where the cable is. And they said, well, that will cost you 12,000 kroner. So since my wife works for Copenhagen University, she has a employer-paid internet connection. She's a system administrator in the ancient DNA bioinformatics group. So we ended up with 2 cable modem. But that shouldn't be a problem, should it? So we have the StofaNet here. We have one modem, we have another modem. Then bridge mode, of course, we do our own firewalls. We have a switch, 2 VLANs through the fiber, 2 firewalls. Piece of cake. Or so I thought. So if we ping from, say, Copenhagen University to my wife's firewall, we have no packet loss. If we ping from her firewall to the exact same machine at Copenhagen University, we have 50+% packet loss. Your task is to explain this while I go through the rest of the slides. So one of my projects right now is that we ordered all the windows and doors with magnetic contacts, so you can see if they're open or closed. Because I want a little light next to my front door that says, oh, you have an open window. So I know that I'll remember to close it before I leave the house. So I have all these contacts throughout the house, and they come up under the attic. And they're connected in one long serious connection. So the idea is, at room number 1, we'll put a resistor across all the switches in that room, another resistor for the next room, and so on. And so measure the resistance. And then be able to tell what rooms have open windows. So the task here is to find 13 resistors that allows us to tell all the rooms apart, single, and preferably also 2 different rooms. And by optimal, I mean the cheapest possible measurement of the resistance. In total, there are 169 combinations. And by optimal, I mean the 2 largest resistances I have to measure divided by the smallest difference I have to measure is as small as possible. And I thought, that's a small matter of programming, right? And started a computer counting. And remember that dual socket epic I told you about? It's been at it for a month. This is a variation of the knapsack problem that explodes very badly. But I have my solution now. But it's a nice little misestimation on my side how large this task actually was to calculate. I didn't bring the gadget I wanted to show here. I'm sorry about that. I came out of bed at 3:45 this morning. I'm immensely proud I remembered to bring my passport. So, in the Department of Random Observation, a house built according to the new Danish building code is very quiet. All this thermal insulation also insulates from sound. We have built our house a little bit more solid than you'd normally do it because we have the railroad running about 60 meters behind the house. The main railroad through Denmark. But I hadn't expected to have to pay attention to how much the fridge would generate noise. I should have done that. Because that is actually the most noisy thing in our living room is the fridge, which gargles and bubbles and burbles and whatever it does. And we bought a 43 decibel fridge. It's like, whatever, right? No, we should have gone for low noise. That's one thing I hadn't expected to see. We also put the washing machine and the dryer a little bit too close to the living quarters. They're even more noisy. That was one of the things that blindsided me. The other thing is that we'll have to start building active cooling in Denmark. We just had a wonderful heat wave to demonstrate the fact. Thermal insulation works both ways, which means that once your house gets too hot, it stays too hot. We use what's called energy windows in Denmark. They let visible light in and out, but infrared radiation cannot get out, which means when the sunlight comes in, if it hits something white and gets reflected out, that's fine. If it hits something dark and gets converted to heat, your living room gets 26 degrees hot in a matter of days. And we moved out to the beach house without drawing the curtains. That was a mistake. In the future, we will need air conditioning in houses in Denmark. We should plan that in the building code at this point. Cooling using the floors is very problematic in Denmark because of the humidity. You will almost, by guarantee, get condensate, which is not good for wooden floors. We built our house with what's called heavy interior walls. It's light concrete, which is about half the density of normal concrete. That helps smooth out the temperature over the day, but not really long range, doesn't do that much there. This is the ventilation system. There's a heat exchange on the ventilation system, which means it can actually actively cool the air and heat the air. When it's too hot inside and the outside air is even hotter, the heat exchanger means that the air you blow out will cool down the air you blow in to not heat the house more than necessary. In the winter, it's the other way around. But you can also have a bypass where you couple the heat exchanger out so that on a summer night when the air outside is cool, you can blow that cool air directly into the house to cool the house down. And this brings us to the intelligent house. Everybody will try to sell you intelligent house, ventilation, heat pumps, switches, doorknobs. It's all crap. None of it talks to each other. And none of it has the control options you will want. I was surprised how crappy all that stuff was. The heat pump came with an internet attachment unit, and there was 4 screws, so I unscrewed them, and there was a Texas Instruments evaluation kit inside the box. I was like, I don't want this. The intelligent house doesn't exist at this point in time. I would drop all IoT options. It's all crap. All the stuff I've seen in relation to this house building project has been crap. And some of it has been really, really crap. I insisted on getting Modbus RS485 communication on everything. The heat pump, the ventilation, the floor heating system control. I put up a lot of electricity meters with Modbus also. And then I roll my own control of it. None of the other stuff coordinates in any way. You cannot do that. So if you're thinking about building a house in Denmark, my first advice would be don't. Most of the houses we build right now will not last more than 30 or 50 years. And that's not very ecological. The way we build houses right now is pretty shitty. They will generally have thermal problems in a hotter climate. They're not built to have air condition, and they're not built so you can add air condition later on. And there's a very strict focus on energy use, which is wrong because we have to start looking at where the energy comes from. Wasting energy from solar panels is fine. Nobody dies because you waste energy from solar panels. We have to look at what kind of energy, when do we use it, what do we use it for? At least in Denmark, we have this very big focus that wasting energy is like, the 8th deathly sin, right? Wasting energy. We have to save energy at any cost. And it's simply not true. If my solar panels are up there and I waste some of that energy, too bad. There's no cost associated with that. So if you want to build a house and you insist on building a house, typehuse, as we call them in Denmark, standard houses, they're very marginal, very unflexible discount goods. What you will see is always the minimum viable product. The shittiest house they can offer people to live in, and then you'll have to add 10 to 15% to that to get a reasonable house. And you'll still end up with a pretty shitty construction at the end of the day. Many of these houses, you cannot add another doorway in them. You cannot remove any of the interior walls. They're all part of the stabilization of the house. In one of the ones I looked at, the walkway on the attic was part of the stabilization of the house. They're really optimized. We're talking highly optimized industrial products. They've cut everything away they can cut away to cut the price down. And there's a lot of plastics in them, untested plastics. We don't know what the lifetime will be, but a good guess is 30 to 40 years. And none of them are easy to change at that point. You'll have plastic under your concrete floor. There's no way to upgrade it, change it. The air tightness barrier is plastic. You can probably change that by tearing down all the ceilings. Maybe also all the interior walls, depending on the construction. And there's still a lot of, we didn't think about that kind of mistakes in modern house building in Denmark. We've always said in Denmark that you have to bury something where it doesn't freeze 120 centimeters. Except if it's a heated construction, 90 centimeters fine. And heated constructions would be the foundations of a house because they were not insulated. Well, guess what? Now they are. Which means that 90 centimeters is not enough foundation for a new house in Denmark. You have to dig it into 120 centimeters. And there's still people doing 90 centimeters foundations in Denmark because they haven't thought about this yet. I was kind of dismayed about the amount of do as we usually do in this. Then you can take a model house and upgrade it, but it's not worth the money. Most of the upgrades you can have is finish. Nicer tiles, gold-plated faucets, whatever, downlight spots in the cupboards, stuff like that. But the basic physics of the house is still the same shit. The shell we built to live in is not worth it. These upgrades are known in the business as the wife bonus, right? So the man decides that we'll go with this company and take this model. And then the wife comes in and says, I want these nicer tiles and I want these. And if she's pregnant, it's even better, right? If you want to build a custom house that's more expensive, doesn't have to be much more expensive, but it is more expensive. It's slower, and you're 100% dependent on whoever you get to build it for you. You have to find somebody good to build it. And even then, money cannot solve all problems. Not that I have enough money to have tried that, but some of the problems I tried to solve with money could not be solved with money because they're still very busy. There's a lot of busyness in the business, so they're used to hurrying, so they will hurry. even if you want them to slow down and do a good job. And there's still a lot of do as we usually do things. And there's pretty shitty building materials on the Danish market, even down to bricks, which these days have a lot of fly ash in them and stuff like that. There are a few places you'll have to accept materials which are suspect. For instance, the ventilation barrier in the ceiling. Either you can do it in concrete or you can do it in plastic. That's the only two options you have. And concrete is generally not what people want there. So if you want to build, this is what we did. Foundations 120 centimeters. We put foundations under all the interior walls to break up the resonance in the floor because we have the railroad that close on. I would at least put foundation under some of them, because otherwise you have this one large concrete slab that can give you a resonance around 1 or 2 hertz, which is really annoying. I didn't put plastic insulation under the floor. I put lacquer, these ceramic things. I don't know what they're in English. We put floor heating in the wooden layer, not into the concrete, because in the wooden layer it regulates much faster, which is important when you have a well-insulated house. No plasterboard at all. They come with built-in fungi spores from the factory, because the cardboard they use is second-hand cardboard, which has been behind the supermarket for a month before it gets driven away. We built heavy inner walls, light concrete is called, half density of normal concrete. That helps a lot on the thermal stability, and it helps a lot on the noise stabilization. Try to avoid interior walls with a stabilizing for the house, because you can't move them afterwards. Make acoustic ceilings in large rooms, not wooden ceilings, but some acoustic damping material. We use something called Trolltect, which is sort of like hay dipped into concrete slurry. The under your ceiling tiles, you have a roof when your tiles break. Normally that's just a plastic foil. Avoid that, they have 10-year lifetime. Put down plywood with a tower on it, and then your ceiling tiles. Increase the dimension of your ventilation above the legal minimum. You will need it. And make sure you have active bypass. And put a lot of electrical outlets all over the place. You will get offered the bare minimum, and they will not be where you want them. For instance, these days we hang our televisions on the wall. You will want an outlet to feed that television somewhere near where you are going to hang it. We ended up costing 17.5 to 18,000 kroner per square meters. It's a little bit hard to make the math here, because some of the rooms of my company, and they have a different cost structure. But that's the cost we ended up net is in that area. That's probably about 25% higher than what a standard housing company will offer you a house for. But you get a lot for that 25% extra money in building quality. I believe the house we built will last for at least 100 years, which makes it a lot more ecologically sound than having to scrap it in 30 years. And most of all, the company you get to build your house, if you hear anything negative about them, don't go with that company. Find a company that nobody's going to criticize. Or the only thing you can accept they criticize them for is they're very busy. We were very lucky. We found a local company. We couldn't find anybody who would say anything nasty about them. To the extent that when we had the contract, I went to the lawyer. The first thing the lawyer said, "You'll love this. They built my house too." I can highly recommend them. The bad news is they're only built down in our end of Zealand. They won't come to Copenhagen. So the Sherlock Holmes internet thing. Anybody has a solution? Yeah?
The DSL is too close, your mode is too close to the DSL, so you don't have a good, a usable signal.
Nope. That's not it. So the problem is the head end spits out a lot of ARP packets all the time to see if people turned off their modems and blah, blah, blah. And the switch only has one MAC table. It doesn't have a MAC table per VLAN. So it will see the head and come in on two interfaces. So when you ping from the outside, the packet comes in and it sees the head end on interface 1, and you send the response back on interface 1 almost immediately from your firewall. So the MAC address entry is still the right place. When you send the ping packet out, it takes 34 milliseconds before the reply comes back. And there's a 50 chance that the MAC table says it's on the other one now. So it will send out your packet through the wrong modem, and the head end will reject it. And apparently, a lot of switch chips only have one MAC table, and it's not per VLAN. This was a particular Atheros chip. And I guess we should have done it that way. The solution for us was that we moved one of the modems down to the house instead, using the coax cable. So that solved the problem for us. But it's the weirdest network problem I've had in at least 15 years. Having different ping losses in different directions. That one took me some time to figure out. Questions? We probably have 2 minutes for them.
Did you use your company firm for heating?
Oh boy. That's a very long story. Okay. But basically, I ended up talking to a senior officer in the Energistyrelsen who explained to me that we have these rules because we have these rules, and we have to follow these rules. So the easiest thing you can do is build two houses right next to each other. Because the heat generated in my company has not paid the same energy tax as the heat inside the house. So if any of that heat leaks into the house, that would be tax fraud. So basically, I have an exterior wall between the company rooms and the rest of the house. I have a wall this thick inside the house because of this. So strictly speaking, every time I open the door, I commit tax fraud. This is utterly insane. But it's nothing compared to what it took to get the sewers done for the house, but that's an entirely different...
No more questions? Oh.
So it's a follow-up on that. So could your company own the property and your family rent from the company?
Yes, that would be perfectly legal and generate a lot of paperwork and make no difference at all at the end.
Okay, also not for the heating because it's the
no. I would still have
tenant.
I would still have to install a heating meter on the hot air leaking through the door.
Because that's going to a tenant and
in Denmark. Yeah. In Denmark, we have both kinds of lawmaking, both taxes and fees. It's just stupid. It's plain stupid. It means you can have a supermarket dumping a lot of heat from their cooling facilities, and you have a bunch of apartments upstairs burning electricity to heat their apartments. And they can't reuse it because tax reasons.
Okay, let's give a big round of applause for Poul-Henning.